Okay, so here, let's try and find the GCF of x squared plus 3. You know, I am going to demonstrate something here, don't worry. Well, we have x squared plus 3. Okay, well, first notice that since there's a non-zero constant term, meaning there's a term with no variables in it, the smallest exponent of x, we can take it to be 0. We can take m to be 0. I mean, again, that's not really precise. We just say that the GCF doesn't have x in it. But you could take m to be 0 here with me. Also, the coefficient of x squared here is 1, right? As you can see, the coefficient here is 1. So that's good. Okay. Well, since the coefficient is 1, right? What's the greatest common factor of the coefficients and the constant term? What's the greatest common factor going to be? Well, the only factor of 1 is just 1 itself. Okay? And the factors of 3 are 1 and 3. So the greatest common factor has to be 1. So B has to be 1. So again, since here this coefficient is 1, that tells you B, the greatest common factor of the coefficients and the constant, is 1. Excuse me. So we get B has to be 1, and the GCF of this thing is 1. That's actually no accident. Mostly because this came about when we factored out a GCF from the original. So the fact that this is 1 is no accident. In general, if you actually factor out the GCF of the original polynomial, the polynomial you get left over has to have a GCF of 1. And that's actually what we did here, right? This was all the polynomial that we started with. We found the GCF, we factored it out. The polynomial here, which is what's left over, this has to have a GCF of 1. It's no accident. Okay, that's good. And these are just some other facts that come about. I mean, if you think about it, they're really, I don't want to say obvious, but they're easy to see. If there's a non-zero constant, then again, the GCF can only be a number, m is 0. Mostly because there's a term there with no variables. And just like what we did here, really, if you have a coefficient is 1, so if a coefficient here is 1, right, then B has to be 1. The greatest common factor of the coefficients and the constant term must be 1. If a coefficient is 1, or if a constant term is 1. And in fact, if you have a polynomial, it has a non-zero constant term, which is 1, then you're done. The GCF has to be 1. It's kind of like, well, maybe not here, but it's really not terribly hard to see, mostly because, again, it's a term with no variables, so m has to be 0. And since the constant term is 1, well, the only common factor 1 has with anything is 1. So that forces the GCF to be 1. Just some things to point out, you know. If you don't memorize it, that's fine. Here's actually an example illustrating that. If we were to find the GCF of this, right? Well, again, there's a non-zero constant term here, a term with no variables. So the smallest exponent of x is 0. There's no x's here, so we take the exponent to be 0. M is 0. Okay. That's good. I mean, again, you know, it's probably not best to write this. It's just for now. I think it's okay because it's a way to remember it. Okay. Now, what about the coefficients and the constant term? Well, we have 4, we have 8, and we have 1. Right? We have 4, we have 8, and we have 1. Okay, so what are the factors of 4? 1, 2, 4. What are the factors of 8? 1, 2, 4, and 8. And the only factor of 1 is 1. So the only common factor is 1. So B has to be 1. That is the greatest common factor among the coefficients, and the constant term is 1. So we get M is 0, B is 1. That forces the GCF to be 1. This is what I was trying to say before. On this slide, this is what I was trying to say. So we have this example. Okay. Are there any questions on this? I mean, that's the GCF. That does give us one way to factor a polynomial. It might be the only way. That can happen. But it's good to have different techniques at your disposal. In fact, if we have a trinomial that looks like this, we have a different factoring method. A trinomial, again, 3 terms. So if you have a trinomial that looks like this, a polynomial that looks like this, the leading coefficient is 1, its degree is 2, you have b times x and you have plus bx plus c. They do go a little bit more into the book about this, but when you factor it, it turns out you have to find numbers b and d so that this happens. In other words, to factor this, you want to find 2 numbers b and d, little b and little d, that is, so that this happens. So they fill in the blanks. So C is their product, capital B is their sum. I know that's a little confusing now, but Monday we'll go more Monday we'll go more into that, and it will make sense. What I'm trying to show you here, I guess I'm trying to illustrate why that's true, or the idea behind this technique. All right.